Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hi there, Herman and Corn. So we've talked on this podcast before about, I've mentioned many times, I'm very interested in speech tech. I think it's one of the best things to come out of the AI revolution, frankly, Transformers. Whisper is, I think, if OpenAI did only one thing and open source Whisper, it would have been, they've done a tremendous service to accessibility. And, everyone likes to have a pop at big tech. And I think sometimes they don't get credit for the things they do that are really wonderful, and which took deep pockets. And Whisper is outstanding. It's an excellent ASR model that has been basically, I'm going to say, pretty much changed my work life from being, sitting at a computer typing every day to using transcription in every way that I can on my phone, on my desktop. And the other side of voice tech is text-to-speech. And it just occurred to me today that this podcast, which is created with TTS, I haven't actually asked for information about it. The voices of Herman and Corn, close your ears for a second, is generated using Chatterbox, which is a TTS engine by Resemble. And it does something using single-shot voice cloning. So I recorded myself talking like Herman Poppleberry and Corn, while my wife wondered what kind of person she married. And that clones the voice, and then I give it text, and that gets generated. And watching the generation process, we're using Modal for its serverless GPU, is really interesting because you can watch the logs, and it's basically a segment-by-segment generation. So every time Herman speaks and every time Corn speaks, those embeddings are cached, the embeddings of the voice clone, the numeric representations, as we've talked about so many times, so that it doesn't have to do that process every single time, but it just generates it one by one. Now, my question is about how this technology works. TTS is kind of counterintuitive because you would have thought that if you give more training data, you're going to get a better result. I have tried to clone my own voice for pranks, and I didn't get very good results. As you know, I'm from Ireland originally. I have an Irish accent, and I recorded an hour of training data, just me speaking random things, thinking that, if this should do it, and I couldn't get rid of that American accent. It wasn't me. I worked with a couple of authors who were doing voice clones for interactive experiences for their books, and I wasn't that impressed either with their voice clones. I thought I did a better job myself on 11 Labs. So TTS and voice cloning is very much imperfect, but at the same time, if we take the voice cloning complication out of the picture, just the process of getting natural sounding text, natural sounding speech synthesized is pretty good. 11 Labs is good. There's Microsoft Edge TTS, and there's a long tail of really interesting projects you see mostly on Hugging Face, Kokoro, XTTS, engines that are trying to do this well. Now, the difference between a bad TTS and a neural TTS is light and day. Those robotic announcements that you'll get from stuff like Piper are painful to listen to. It doesn't sound anything like a human. But a lot of the 11 Labs voices are delightful to listen to, and it means you can listen to anything that you want using audio. So there's an assistive use case, and I think there's just a enjoyment use case. I think that audio is a really nice way to consume content, and I would regard the creation of this podcast as maybe my proudest AI experiment to date. It's taken about a year, as I mentioned, of tinkering to get this pipeline generating episodes that I think are good and that I enjoy listening to. But the magic really is in the TTS, and I've tried a lot of different engines, seen a lot of different results. So Herman and Corn, I'd love to ask how neural-based TTS, this better TTS we associate with 11 Labs and those companies, how it actually works under the hood. How does it go from, taking written text, and how do those accessory models, when you have text that isn't TTS-able, let's say that I write something like asterisk, or I don't do a great job at at pre-formatting. Some of them now are smart enough that they can work around that, and some of them are good enough that they can infer prosody. Prosody is a very important topic in TTS, referring to that kind of emotional cadence of speech. And when I'm giving something a text and it can infer, this is a heading, we should read it out more slowly and more, with a slightly different voice, and this is paragraph text, when the models do guess that, it makes a huge difference, and that's really something that's key as well. We can talk as well, maybe another time, about real-time TTS. That's another use case. But I'm personally much more interested in the long-form TTS, the kind of TTS that makes this podcast work. So Herman and Corn, explain to me how text-to-speech works, and all the other things that are needed to make it successful. What tips would you give for someone like me who is creating AI workflows using TTS and wants to get those good results consistently and at a price that isn't going to break the bank on API charges, GPU serverless, or whatever else we're using for generation? Herman and Corn, over to you. Text to speech in 2026.
Welcome back to my weird prompts. I am Corn, and today we are getting a little bit meta. It is January 8th, 2026, and if you have been listening to us for a while, you might have noticed that my brother and I sound, well, pretty consistent.
Or maybe too consistent, depending on who you ask. I am Herman Poppleberry, and today is a special one, because we are actually addressing the very technology that allows us to exist in your ears. Our housemate Daniel sent us a prompt about speech technology, specifically text-to-speech and voice cloning.
It is funny, Daniel lives right down the hall from us here in Jerusalem, but he still sends these audio prompts in like he is a long-distance correspondent. He was talking about how he has been using tools like Whisper for transcription and Resemble for generating our voices, and he is curious about what is actually happening under the hood.
It is a great question. We have come such a long way from the robotic, stilted voices of the early 2000s. If you remember the old navigation systems or the early accessibility tools on computers, they sounded like a toaster trying to read the dictionary. But now, in 2026, we are at a point where, in many cases, the nuance can be very close to human speech.
Right, and Daniel mentioned he tried to clone his own voice, specifically his Irish accent, and he struggled with the model defaulting back to an American cadence. So, Herman, let us start there. How did we get from those robotic phoneme mashers to neural-based systems that can actually infer prosody and emotion?
That is the big shift, Corn. The old systems were what we call concatenative synthesis. Basically, they had a massive database of a single voice actor recording every possible sound combination in a language. When the computer wanted to say a word, it would literally stitch those tiny audio clips together. It was technically accurate, but emotionally dead because there was no flow between the sounds.
Like a ransom note made of magazine clippings, but for your ears.
Exactly. There was no co-articulation, which is the way our mouths prepare for the next sound while finishing the current one. Neural text-to-speech changed everything by moving away from stitching clips to what we call generative modeling. Instead of a database of clips, the model learns a statistical representation of what speech sounds like. Alongside transformer-based approaches, there has been growing research into alternative generative methods like diffusion and flow matching, and some experimental models in the F5TTS family explore these ideas.
So, when we talk about a neural model for speech, are we talking about something similar to how a large language model predicts the next word?
Very similar. In fact, many modern systems use a transformer architecture, just like the one behind the major language models we use today. The process is usually split into two main parts. First, you have the acoustic model. This takes the raw text and converts it into a visual representation of sound called a MEL spectrogram.
I have seen those. They look like heat maps of audio frequencies, right?
Precisely. The MEL spectrogram captures the energy at different frequencies over time. It is essentially a blueprint for the voice. The neural network looks at the text, understands the context, and draws this blueprint. Then, the second part, called a vocoder, takes that blueprint and turns it into actual audio waves that your speakers can play. However, some of the newest end-to-end models, including systems like GPT-4o, move away from the classic MEL spectrogram plus separate vocoder pipeline and instead generate audio through a more integrated representation, closer to predicting waveforms directly from text and conditioning signals.
Okay, but the magic Daniel was asking about is the prosody. Prosody is the rhythm, the stress, and the intonation of speech. How does a model look at a sentence like, "Oh, I do not know. I never said she stole my money," and know which word to emphasize? Because that sentence has 7 different meanings depending on where you put the stress.
That is where the deep learning aspect becomes so powerful. In 2026, these models are not just looking at the words, they are looking at the semantic embeddings. When the model processes a sentence, it creates a mathematical representation of the meaning. It realizes that if the sentence ends in a question mark, the pitch should likely rise at the end. If it sees an exclamation point, it increases the amplitude and the sharpness of the onset of the words.
But it goes deeper than just punctuation, does it not? I mean, we do not always punctuate our speech perfectly.
It does. Modern models use something called attention mechanisms. While the model is generating the sound for the 3rd word in a sentence, it is still looking back at the 1st word and ahead to the 10th word to ensure the emotional arc is consistent. It is essentially simulating a mental model of how a human would breathe and pause. Some of the most advanced models even have latent variables for style. You can tell the model to be whispered or angry or excited, and it adjusts the entire generation to match those parameters.
This brings me back to Daniel's Irish accent problem. He said he recorded an hour of training data, but the model still sounded American. Why does that happen? If the model is supposed to be cloning his voice, why is it leaking another accent?
This is a common issue with what we call foundation models. Most of the high-end text-to-speech engines today are pre-trained on tens of thousands of hours of speech data. Because the vast majority of high-quality, labeled audio data on the internet is American English, the model develops a very strong prior, or bias, toward those speech patterns. This is often called the average voice problem.
So, even if you give it an hour of Irish audio, it is trying to fit that audio into a box that was built for a Californian or a New Yorker.
Exactly. It is like trying to paint a portrait with a brush that only wants to make certain strokes. The model sees the Irish phonemes, but when it goes to predict the prosody, the rhythm, it defaults to the patterns it learned from that massive 20,000-hour dataset. To fix that, you usually need a process called fine-tuning, where you tell the model to prioritize your specific data over its pre-existing knowledge. But even then, if the foundation model was not trained on a diverse enough set of accents, it might struggle to reproduce the specific lilt of a Dublin accent. In 2026, some newer zero-shot models that explore flow or diffusion-style training show promising results and can sometimes avoid the strongest American accent bias. But
that is fascinating. It is almost like the model has its own native language, and it is trying to speak Daniel's voice with a heavy American accent. Now, Daniel also mentioned the workflow side of things. He is using Resemble and Modal for serverless graphical processing units. For someone trying to build a high-quality workflow without spending a fortune, what is the state of the art right now?
The landscape in 2026 is actually quite varied. You have the high-end API providers like 11 Labs and Resemble, which are fantastic for ease of use. They handle all the heavy lifting, the hosting, and the complex inference. But as Daniel noted, the costs can add up if you are doing long-form content.
Right, because you are paying per character or per minute of audio generated.
Exactly. If you want to move towards something more cost-effective, you have to look at self-hosting or using serverless infrastructure like he is doing. There are some incredible open-source models now. We have seen projects like Bark, XTTS, and more recently, the Kokoro models, which are incredibly lightweight. Some of these can run on a standard consumer-grade laptop and still produce near-human quality. Kokoro is particularly impressive because it is a relatively small model, on the order of tens of millions of parameters. Yet many listeners find its quality competitive with much larger systems in informal tests.
Daniel mentioned something interesting about caching embeddings. He noticed that every time you or I speak, the system uses a numerical representation of our voice clone. Can you explain why caching that is a big deal for performance and cost?
That is a great technical catch by Daniel. When you use a zero-shot voice cloning system, the model has to look at a reference audio clip of the target voice, say a 10-second clip of me, and turn that into a speaker embedding. This embedding is a long string of numbers that tells the model exactly what my vocal characteristics are: the rasp, the pitch, the resonance.
And if you are generating a whole podcast, doing that calculation for every single sentence is a waste of energy.
Precisely. If you are generating 1,000 sentences for an episode and you calculate that embedding 1,000 times, you are burning through graphical processing unit cycles for no reason. By calculating the embedding once, caching it, and then just passing that small piece of data along with each new text string, you can significantly reduce the latency and the compute cost. It makes the whole pipeline much snappier. On a platform like Modal, that can noticeably reduce your compute usage and monthly bill, sometimes by a substantial margin, depending on your workload.
Let us talk about the quality versus cost trade-off. If I am a developer building a tool that needs to read articles aloud, or maybe an interactive AI assistant, how do I decide between an expensive API and a self-hosted open source model?
It really comes down to your requirements for latency and emotional range. The high-end APIs are still the king of prosody. They are very good at inferring that a sentence is a joke or a sarcastic comment. If your application needs deep emotional resonance, the premium API PIs are usually worth the cost. However, if you are doing something like reading technical documentation or news summaries where the tone is relatively flat, the open source models like Kokoro or F5TTS are more than sufficient.
And what about the hardware? Daniel mentioned Modal, which is a serverless platform. Why go that route instead of just renting a dedicated server?
Serverless is perfect for audio generation because the work is often bursty. You might need to generate 10 minutes of audio all at once and then nothing for an hour. If you have a dedicated server running 24/7, you are paying for it even when it is idle. With serverless graphical processing units, you only pay for the seconds the model is actually running. The downside is something called cold starts.
I remember we talked about this back in episode 206 when we were discussing AI benchmarks. A cold start is the time it takes for the system to load the model into memory before it can start working, right?
Exactly. For a large speech model, that might take 10 or 15 seconds. If you are building a real-time voice assistant, a 15-second delay is a deal breaker. But for a podcast like ours, where the generation happens in the background before the listener ever hits play, cold starts do not matter at all. That is why Daniel's setup is so smart for this use case.
So, if someone wants to replicate this, they should look at a pipeline that uses a fast transcription model like Whisper for the input, and then a cached embedding with a neural vocoder for the output. But how do we make it sound less like a reading and more like a conversation? I noticed that sometimes TTS models can sound a bit breathless or they do not know when to take a beat.
That is where the pre-processing of the text comes in. A lot of people just dump raw text into these models and hope for the best. But if you want that natural flow, you need to use something called Speech Synthesis Markup Language, or SSML. It is a bit like HTML for audio. You can manually insert tags that say, break for 500 milliseconds here, or emphasize this specific word.
That sounds like a lot of manual work, though. Is there a way to automate that?
In 2026, we are seeing large language models being used as the director. You can take your raw script and pass it through a model like GPT-4 or a specialized smaller model and tell it to add SSML tags based on the context of the dialogue. It can identify where a natural pause would be for a breath or where a character would be interrupted. It is essentially giving the speech model a set of acting notes.
That is such a cool concept. The language model understands the emotion, and the speech model executes the sound. It is a two-stage process of understanding and then performing.
It really is a performance. And that brings us to the future of this tech. We are moving toward what is called end-to-end multimodal models. Instead of having a separate text model, a separate acoustic model, and a separate vocoder, we are starting to see single models that can take in text and output raw audio directly.
Like the GPT-4o model we saw glimpses of, where the latency is so low, it feels like a real-time conversation.
Exactly. When you remove the boundaries between these stages, the model can maintain much more of the nuance. It does not lose information as it passes data from one part of the pipeline to the next. The prosody becomes much more organic because the model is predicting the audio waveforms directly from the meaning of the words.
I want to go back to the ethical side of this for a second. Daniel mentioned he was doing this for fun and for the podcast, but voice cloning has a bit of a reputation. What are the safeguards in 2026?
It is a major topic of discussion. Many leading commercial providers now advertise consent and verification safeguards. For example, some require you to record specific scripts or confirm you have rights to a voice, and they prohibit cloning public figures, although exact policies and enforcement vary by provider. There are also digital watermarking technologies being integrated into the audio itself. These are subtle changes to the frequencies that a human cannot hear, but a piece of software can detect to prove that the audio was AI generated.
Like a digital fingerprint hidden in the sound waves.
Exactly. We discussed something similar in episode 146 when we were looking at AI guardrails. It is a cat and mouse game, but the goal is to make sure that as this technology becomes more accessible, it remains clear what is human and what is synthesized.
So, to summarize for Daniel and anyone else building these workflows, if you want high quality and low cost, you should look at caching your speaker embeddings, using serverless infrastructure for your heavy lifting, and maybe using a language model to add some performance notes to your script before it goes to the speech engine.
And do not be afraid to experiment with the open source models. The gap between the paid APIs and the top-tier open source projects is closing faster than anyone expected. If you have the technical chops to set up a container on a platform like Modal, you can get very close to 11 Labs quality for a fraction of the price.
And hopefully, by this time next year, those models will have a better grasp of the Irish accent, so Daniel can finally hear himself properly.
One can only hope. It is all about the data, corn. As more diverse datasets are open-sourced, these models will get better at representing the whole world, not just the folks in Silicon Valley.
Well, this has been a bit of a trip, talking about our own digital guts. It makes me appreciate the work Daniel puts into making us sound as good as we do.
It really does. I feel quite polished today, I must say.
You always do, Herman. You always do. Before we wrap up, I want to remind everyone that if you are enjoying our deep dives into the weird and the technical, we would really appreciate it if you could leave us a review on your podcast app or on Spotify. It genuinely helps us reach more curious minds like yours.
It really does make a difference. And remember, you can find all our past episodes and a way to get in touch with us at our website, myweirdprompts.com. We love hearing what you want us to explore next.
Huge thanks to Daniel for sending in this prompt. It was a fun one to tackle from the inside out. This has been My Weird Prompts.
I am Herman Poppleberry, and we will talk to you next week.
Thanks for listening. Stay curious.
That was a good one, Corn. Do you think they realized we were talking about ourselves the whole time?
I think they have a pretty good idea, Herman. I think they have a pretty good idea.
Fair enough. Let us go see what Daniel is cooking for dinner. I smell something good.
Probably just more data for the model, Herman.
Very funny. See you, everyone.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox Turbo.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.